Welmo2017. Today I'm trying to explain you our road marking machine design. We walk from standard internal combustion engine. We walk from standard internal combustion engine and turn it into an electrical vehicle. We use the same basic structural design and improve it. Now it's a bit different. So today, as you can see, mainly we use internal combustion engines on road markers, but there are many problems. They are noisy. They are giving us so much fumes, and also again at nighttime use, people don't want this kind of noise near their houses, so it's a bit don't be liked by people that live in there. So we try to improve it and turn this internal combustion engine vehicle into a different thing. So what we did was start from the current design. The user requires from us is this vehicle should go 4 kilometers per hour, even if it's climbed on a slope. And the slope degree is 9 degrees or 16% angle, and the current mass is 2.3 tons. We should keep the 9 degree slope and 4 kilometers per hour data. Also, they can fuel it on the road, but the customer requires from us at least 4 hours of continuous working with full painting capabilities and everything. So, cover 9 degrees of angle, work for 4 hours, and able to climb 9 degree slope while painting with 4 kilometers per hour speed. So, first we run a pre-designed calculation, and we add some safety weights. We put up the 2.3 tons of mass to 3.5 tons of mass, because we are using batteries and also cables and drivers and stuff. Also, we plan to add solar panels in this calculation. I took the air drag 0.6 and the projectile areas. We didn't change the mechanical structure, so it's the same as a vehicle. We use the same tires, so all those that are the same. There you can see input data. So we use the tire resistance formulation, wind resistance formulation, and for climbing, we're gonna calculate it for 2 speeds, but same angle. Sorry. Okay. First of all, for 10 kilometers per hour, this is current maximum speed. The vehicle can go up to 10 kilometers per hour on a flat road, not by climbing, but to give us a ballpark information about how much power we might need. We also calculated for 10 kilometers per hour and also 4 kilometers per hour, both. So by using the previous formulations, or you can see it from here, same angle, since alpha is for 9 degrees in gradient. Climbing usage in total 16.8 kilowatts maximum power, but 6.7 kilowatts nominal power in 4 kilometers per hour if we are climbing up a hill. So 6.7 kilowatts while climbing up a hill means 6 kilowatts nominal motor output as adequate enough. So on line 13 you can see chosen motor. It's a brushless DC motor, can provide more than 6 kilowatts at 90% efficiency. So here we calculated the torque. Okay, we have enough power, but if we have enough torque, we don't need any reduction. But if we don't have it, we might need a reduction. Also for speed, So again, calculated the torques. So for our normal and maximum pre-design, we need this calculated, those are calculated torques. We need formulation. So we only use pre-design calculation after that, and we choose our reductor that can give us 1/52 condensation ratio. So after selecting the motor and after selecting the reductor, we redesign it. Actually, the customer only requires us to go 4 kilometers per hour while climbing, so we don't need that much of a power. Again, nominal power calculated as if it's on flat load, and a maximum power by using this motor, this brushless DC motor, and not to go over less than 70% efficiency. We choose 7 kilometers per hour top speed while climbing to calculate it. And so on a flat road, we are using less than 1 kilowatts, but while climbing 8.4 kilowatts. Again, let me show you. Our motor can provide around 13 kilowatts if needed, with less efficiency than 90%, around 78%, but can provide it. So here we calculated the motor requirements, and yes, the motor can give us our required powers and speeds. There are additional powers. This is not a road vehicle. This is a road marking vehicle. So we need to use some paint pumps and compressors and oil coolers and stuff to run the painting equipment. We calculated their maximum power uses is around 9 kilowatts, but there is a thing that their maximum usage is not run in the real world. In the real world, they are around half of this. So we put this into calculation as if it is half of the maximum value. With 90.3% efficiency, they are running at 3000 RPM. All those additional support system, additional painting system. So we will need 5.12 kilowatts of power as an input for the secondary motor. Here is the battery calculation. In order to use the battery capability fully, we use deep cycle tractional batteries. They are more robust, and you can drain more power in less than 5% can be used sometimes. Our motors are both 72 volts, and our drivers can be supplied with 80 volts. So we choose an 80 volt battery with 600 amperes per hour, and this battery can provide more than 4 hours of usage. While calculating this, in the previous slides, I showed you 2 watts calculation, power calculation. One of them is 8.4, the other one is 0.77. We calculated as if the vehicle is going to use nominal power at 80% of this working cycle. The rest, 20%, is maximum power. This will give us some useful calculation if it's in the real world, because we couldn't build it yet, so we cannot get real data, so we made this assumption. We add 8 solar panels, each with 300 watts. So we calculated with 90% efficiency. We're gonna convert it and store it and stuff. So after 90% efficiency, we're gonna get 4.7 hours, 0.7 hours more time. So I'll say this is a new design. We just added the solar panels. We don't want to change the shape so much because in this industry, people are a bit scared to change the systems, and we don't want to scare the customers of the system. In conclusion, the new design can climb the required slope, can run more than 4 hours. As a single battery pack, if needed, it can be changed with a forklift or something because it's a bit heavy. It has no emission, has no noise, and has no how to say. It only uses today's technology. It doesn't use any high tech. Cannot be found in the market technology. So you can find spare parts easily. And if something goes wrong, if you have some troubles with the operators and stuff, you can change it and you can use the system as if you're using an internal combustion engine. Thank you.
We can get some questions from the audience. Any questions? I will ask a question then, if no one asks. You said there is an extra load for marking the road, right?
Yes.
Around 9 kilowatt. Did you calculate this value using some equations, or did you get this number from literature?
It's those values are the labeled values. They are labeled load values of this oil radiator, this paint pump, or air compressor. But in real-time usage, they are not. The customer doesn't use it at full capacity. This is their full capacity, so to say. We are using empirically. They are using it at half of its capacity. So here it's 9.25 kilowatts at full capacity, but they are using it in real time at half capacity. So we calculated from the empirical values. We didn't use any special formulation.
Yes.
Empirical values we use it. Again, here 99.3% efficiency is all those systems, previously shown systems, are run at 3000 RPM. So our motor is 3000 RPM at that kilowatt is around that. So.
All right. Any more questions? Okay, then thank you again for the presentation. So this concludes the session. So I would like to